Okay, hi guys. So we're going to move on now with question 4. The first part of the video did question 1 to question 3. So now we move on with question 4. So question 4 says, in an experiment to investigate the relationship between pressure and temperature of an enclosed gas, 48 grams of oxygen gas were sealed in a container. The results obtained are recorded in the table below. Okay, so now you can see as we're increasing pressure, as we're increasing temperature, you can see that our pressure is also increasing. You can see that they've given you two sets of values. One of them is going to be the first question says, draw a graph of pressure versus time on the attached answer sheet. Extrapolate the graph so that it intersects the y-axis. Okay, so they've given you these data points. Now you have to choose. Are you going to put pressure on your y-axis or are you going to put temperature on your y-axis? Which one has to go on y and which one has to go on x, okay? So you can see that your temperature has pretty much, it goes up in equal units. It goes 250, 300, 350, 400, 450, which means the temperature was probably the variable that was manipulated by your researcher. Remember the definition between dependent and independent variables. Your dependent variable is the one that you are observing. So you're changing some kind of variable because you want to see what happens to your dependent or observed variable. Okay, and your independent variable is the variable that you manipulate so that you can see how things will change. And usually, when researchers manipulate variables, they manipulate them in equal intervals. They don't say, oh, 250, 271, 384. They don't change the variables by uneven intervals. But you can see that pressure is not increasing in even intervals. So your educated guess should be that temperature is your independent variable because it looks like these are values that have been manipulated by the researcher. These are intervals that any kind of sound minded scientist would choose to increase temperature by. And these ones, however, the change is not as defined. It's not changing by 50 every single time, or 30 or 20. It's changing by slightly different numbers every time. So we can then deduce that pressure must go on the y-axis because it is my dependent variable. It is what I am observing. And temperature must go on my x-axis where my independent variable goes. So if you go have a look at the graph table or the graph paper, oh sorry, not this one, the graph paper that they give you, you can see that they tell you pressure must go on the y, temperature must go on the x. So in a matric paper, they probably won't do that, okay? But you know that you now take these values that they've given you as coordinates. So coordinate number 1 is 155.8 and 250. And you go and you put in, you need to first draw your scale for your graph, and then you go and you draw in each of the points, each of the coordinates. Okay, like I said, you treat these sets of data like coordinates and you plot them all on the graph. And if you plot them out correctly and you extract, these are the points you'll get. Okay, you'll get 250 and whatever this value was on the table. Then the next one is 300. Then the next one is 350. So your intervals for your temperature, as I said, remember they're very spaced out and neat. Okay, but these ones are a little bit more unpredictable. Okay, remember that you need to have a label for your y and x values. You need to have a graph heading, and then you obviously need to correctly insert all of your points. And then these are the points you would have drawn in, and then you will have put your ruler here. And extrapolation means that you don't only connect the points that they give you, but you also extend it backwards until it hits the y-axis because they want a y-intercept for your graph. Okay, so this is what your graph should look like. Obviously, I can't go through drawing this with you. It's a bit tricky on the computer, but this is what your graph should look like after you've plugged in all of your coordinates, all of the data that they've given you. Okay, So the first question after you've drawn your data or your table says, what conclusion can be made from the final graph? Okay, well, what conclusion can we make from this graph? What does it look like? 4.2 says that your conclusions are that pressure of an enclosed gas is directly proportional to the temperature if volume stays constant. And that's the conclusion you can make. So 4.2, so this is the conclusion you can make from this graph. The pressure of an enclosed gas is directly proportional to the temperature if volume is kept constant. Okay, and you can tell that pressure is directly proportional to temperature in this scenario because this is a straight line graph. Okay, it's a straight line graph, and that indicates a linear or directly proportional relationship. Okay, explain why it will not be possible to obtain accurate values at very low temperatures. So this is 4.3. And the reason that you will not be able to determine accurate values at very low temperatures is because so why at very low temperatures can our values not be accurate? And that's because if you push the temperature low enough, gases eventually start to liquefy. Remember, if you take away enough energy from a gas, it starts to turn into a liquid. And it means that none of the answers or any of the experiments that you do will work out the way that they should, because now you're no longer working with a substance that has the properties of a gas. Remember, the properties of a liquid and the properties of a gas are very different. So at very low temperatures, your gas starts to behave as a liquid as it begins to liquefy, and therefore these laws or relationships that we've established will no longer hold true, because the laws and relationships that we have established are exclusively for substances in the gaseous form or the gaseous state. Okay, so that's 4.3. 4.4 says use the kinetic molecular theory to explain the effect of an increase in temperature on the pressure of a gas. Okay, so this one is for 4 marks. So, point number one, if the temperature increases, the average kinetic energy of particles increases. Remember that temperature temperature is directly proportional to kinetic energy, which means that as temperature increases, kinetic energy increases. Temperature and kinetic energy are basically synonymous. So whatever happens to the one has to happen to the other. The more energy or heat I give by increasing the temperature, the more energy my molecules will have. Okay, so for 4.4, your first point is that if temperature increases, average kinetic energy of your particles also increases. Okay, point number two is that when particles have more energy, they move faster. Point number three is that when molecules move faster, it increases the number of collisions that occurs between these particles. And point number four is that if the number of collisions increases, so the pressure increases. So let's just quickly summarize that. So for 4 marks, we're at 4.4 now, okay? And they're saying use the kinetic molecular energy theory to explain the effect of an increase on temperature on the pressure of a gas. So 4 marks, 4 points. Point number one. By increasing the temperature, we increase the kinetic energy of molecules. Point number two is that increasing kinetic energy increases increasing kinetic energy increases the speed at which molecules are moving. Okay, so they're moving faster. Okay, point number three is that so when molecules are moving at a higher speed, this increased speed leads to more collisions between molecules or particles and other molecules, as well as particles and the sides of the container. And our last point is that an increase an increase in the number of collisions that occurs within a reaction vessel results in an increase of pressure. So this is 4.4. These are the four, you can see it's for 4 marks, and these are the four things that you need to say to get all four of your marks. Okay, that's 4.4. Now we move to 4.5. Under which conditions of temperature and pressure will a real gas act as an ideal gas? Okay, so remember, an ideal gas is like an imaginary gas. It's a gas that in nature doesn't really occur. It's a gas that basically only behaves the way it does because under laboratory conditions or kind of simulated laboratory conditions or perfect conditions does it act the way we want it to act. And it's saying when we talk about an ideal gas and how it's hypothetical because it's a perfect gas acting in a perfect environment, otherwise known as a laboratory environment where researchers can control all the variables. They want to know, what do I have to make the conditions in real life so that a real gas, will act as my ideal hypothetical gas? And the answer to 4.5 is, in order for a real gas to act as an ideal gas, you need high temperatures and low pressures. Again, this is a study. These are two study points. You need to know that a real gas will act as an ideal gas at high temperatures and low pressures. So that's 4.5. 4.6, now we calculate the gradient of the graph, okay? So you know that the formula for gradient is often also represented as m equals y2 minus y1 over x2 minus x1. So you need to find 2 points on your graph. Okay, so I'm going to go with my lowest point and my highest point. And I'm going to use these two sets of values to plug into my gradient formula. You already know that pressure went on your y-axis, and you already know the temperature went on your x-axis. So I'm going to say this is going to be y1. These coordinates are going to be, oh, sorry, not y specifically, but let's say these sets of coordinates are going to be coordinate set number 1, and these sets of coordinates are going to be coordinate set number 2. So we say y, let's do it the other way around rather, so that our numbers don't turn. You can do it however you want, it really doesn't matter. But so let's make this set 1, and let's make this set 2. Doesn't matter which ones you make set 1 and set 2, as long as you plug them in correctly, you should still get the right answer. So let's say these are my y values. So I have to say y2 minus y1. So I say 280, because this is my y2 value, 280.5 minus my y1 value, which is 155.8 over my x2 value is 450 and my x1 value is 250. So now you plug that into your calculator. 450 minus 250 goes 200 at the bottom, and 280.5 minus 155.8 gives us 124.7. So now we say 124.7 divided by 200, and that gives us a gradient of 0.62. And that's your answer. So I'm going to leave this here for a while, or let me just zoom out a little bit. Maybe you can have a look, see where you understand. Okay, cool. I think we're good. I think let's keep moving. So we've calculated the gradient of the graph now. Now it says use the answer in question 4.6 to determine the volume of the container. Okay. So you can see that this question is for 5 marks. So it means that you're going to have to do more than one calculation to get to this answer. Okay, and they want you to use the gradient that you've calculated. Okay, so what do we have? They want us to calculate the volume of the container. They've told us that they've given us the pressures, they've given us the temperatures, but the one thing that we don't know is the number of moles of oxygen, because they've given us set out values, right? So we know that we're looking for volume, and we know that they've given us grams, which can be, or a mass that can be converted into moles, which means the most likely formula we're going to have to use to get our answer here is PV equals nRT. So pressure times volume is equal to number of moles multiplied by my constant R multiplied by temperature. Okay, so step number 1 is to convert this mass into moles because we don't have moles. We can use a P and a T from my table. We're looking for V, so we need N so that we can plug in in to get a V value. Okay, so it's very easy to convert a mass into moles. You say small n, which means number of moles, is equal to small m or mass over my molar mass, big M. Okay, so my mass is 48 grams. Grams is the correct SI unit for chemistry. And we divide that by the molar mass of oxygen. It's oxygen gas. Remember, oxygen is diatomic, which means it exists in nature as O2, which means that when we substitute in the molar mass, we go to the periodic table to get our relative atomic mass. You're looking for the relative atomic mass, the value at the bottom of oxygen, which is 16. And it's 16 times 2 because oxygen can't exist as just O on its own. So it's 2 times 16. So now you say 48 divided by 32 gives us N is equal to 1.5 moles of oxygen gas. Okay? And so now we've got our formula. Our PV is equal to nRT. Okay? But this is the formula. But remember, they said they wanted us to use our gradient, our calculated 0.62 gradient. Okay? And remember, when you're doing gradient, you're putting your y over your x, which means in this case, you're putting pressure over temperature. Okay? So, we know that when we manipulate this formula to make the gradient the focus, okay, we can stipulate or specify that gradient in terms of our PV equals nRT formula is equal to nR over V. We have N, we're looking for V, R is a constant, okay, and gradient we calculated. So now, we must just double check quickly though, okay, because remember the gradient we calculated was using kilopascals and Kelvin. And Kelvin is the correct SI unit for temperature. That's fine, you can leave that as it is. But the SI unit for pressure when we're using our PV is equal to nRT formula is pascals, which means we need to convert our gradient value, which we got as sorry, just give me a sec. I just want to find it. I think we got it as 0.62. Yes, we got it as 0.62, right? Which means we need to multiply 0.62 times 1,000. Okay, because to convert from kilopascals to pascals, you multiply by 1,000. I think I might have said that the wrong way around because we're converting from kilopascals to pascals. I said it the wrong way around, but the principle remains the same. Remember that your Pascal value is going to be larger than your kilopascal value. Okay. Um, so we need a bigger value for pascals than we do for kilopascals. So we multiply our gradient by 1,000, so that conversion is correct. So that means our gradient is now 620 with our conversion. Our N is what we calculated here. Our R our molar gas constant is 8.13 joules per Kelvin. So we go down, we multiply by 8.13, 8.31 over the volume. So you plug this into your calculator, you manipulate your equation, and you get a volume of 20.1 decimeters cubed. And that's your final answer. Okay. Now we move on to question 5. So it says, whether balloons are sent into space to gather data. The balloons usually burst at a pressure of 27,640 pascals and a volume of 36.3 meters cubed. The data collector then falls back to Earth. So here they show you a picture. They say the gas in a certain weather balloon has an initial volume of 12.6 meters cubed and an initial pressure of 105,000 pascals at a temperature of 25 degrees Celsius when it is released into space. Calculate the 5.1, the temperature of the gas in degrees Celsius in the balloon when it bursts. Okay, cool. So 5.1, we are going to be using remember, if you're unsure about formulas, you have to go to your formula sheet. The grade 11 papers do not, especially for chemistry, do not have a huge range of formulas. There's way more in matric papers. But you can see we've only got two formulas, okay? They haven't given us any information in this question to calculate moles. So we need to calculate what they're asking us for, which is the temperature, using this formula. Our P1 V1 divided by T1 is equal to P2 times V2 over T2. So we go back down. We know that's the formula we have to use now. So we write it. And also remember, in this scenario, we've got pressure 1, volume 2. Oh, sorry. We've got pressure, volume, and temperature number 1, and pressure, volume, temperature number 2. So there has to be two sets of information when this formula is applicable. So remember, they say to us, okay, well, where the balloons are, the usually burst, okay, blah, 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 and the volume of this. The gas in a certain weather balloon has an initial. So these are our initial values. These are going to be the values we plug into P, V, and T1. So they say to us initially it has a pressure of 105,000 pascals. That's the correct SI unit. Pascals is the SI unit, so we just substitute in. We don't have to convert before we sub in. So 105,000 multiplied by an initial volume of 12.6 meters cubed. Okay, also our SI unit. Okay, over our temperature of 25 degrees Celsius. Now remember that for these formulas, your temperature needs to be in Kelvin, okay? And when you want to convert Celsius to Kelvin, okay, you need to say my degrees Celsius value plus 273.15 gives you your temperature in Kelvin. Okay, so if we have a temperature of 25 degrees Celsius, that is 25 plus 273.15, which means we have a reading in Kelvin of 298.15 degrees Kelvin. Okay, so remember, you need to know what your SI units are. If you substitute them in the incorrect units, you're going to get everything wrong. Okay, so double check that you know what your SI units are for all of the formulas that you're using. Okay, so now that's all of our information on the left-hand side. So now we go and we plug in our information on the right-hand side. They are looking for the temperature that the balloon bursts at. So it means that T2 is going to be the variable that we're looking at. But what can we plug in for our pressure when it bursts? The pressure is 27,640 pascals when it bursts, multiplied by a volume of 36.6, 36.3, and T2 is what you're looking for. So now you need to rearrange this entire equation, and you need to make T2 the subject of the formula so that you can solve for T2. And the answer you should get once you've done that is 226 Kelvin, also known as negative 47 degrees Celsius. Okay, and you convert between Kelvin and Celsius by subtracting. If you go from Celsius to Kelvin, you add 273.15. But if you're moving from Kelvin to Celsius, you subtract 273.15. Okay, so that's the answer for 5.1. The temperature at which it bursts is negative 47 degrees Celsius. Okay? And then our final question is, what was the initial amount of gas in the balloon? So you know that there's only one formula or pressure volume formula that takes moles into consideration. And it just means that we're now using this formula with all of our initial information because they want to know what were the moles initially. So we have to use this, okay? If they wanted moles finally, we'd have to use this. So we just go and we say, okay, well, initially my pressure was 105,000 pascals multiplied by my initial volume, which was 12.6, equal to N is what we're looking for, multiplied by 8.31, which is my R, my constant, which you can find on your formula sheet. Okay, multiplied by my temperature, which was 298.15. Again, you manipulate your equation, you make N the subject of the formula, and you get 534.25 moles. And that's your final answer. Okay, that was for 5.2. Okay, now we move on to question 6. The decomposition of hydrogen peroxide in the presence of a catalyst at standard pressure and room temperature is given by the unbalanced chemical equation. Okay. So remember, unbalanced means you have to balance it. It also in matric, they're never going to tell you that it's not balanced. They don't like you that much in matric. They want you to suffer more. So they'll never tell you that it's unbalanced. You always need to check. That is step 1 of every single question that you write. Okay? Step 1 should always be, if there's a chemical equation involved, I need to check if it's balanced, because in a final year exam, they will not tell you. And if you do all of your calculations using an unbalanced equation, everything will be wrong. Okay, so you're setting yourself up for failure by not making that step number 1. Okay, so it says the oxygen gas is collected at the volume, and the volume is recorded over a period of time. The reaction is completed at time t. The results are plotted on a graph of volume O2 versus time as shown below. Take the molar gas volume as 24.45 at room temperature and standard pressure. 6.1.1, balance the equation. So this is the equation that we are balancing. Okay, guys, I'm having some technical difficulties, so I'll have to continue in another video. Or, no, I think we're okay. Okay, I think we're still okay. Sorry. Just some technical difficulties on my side. Okay, so we're going to start with balancing the equation. So remember, you're trying to make sure that you have the same number of atoms of everything on the left-hand side that you do on the right-hand side. So this side we've got 2 hydrogen and 2 oxygen. And this side we've got 2 hydrogen and 3 oxygen. Okay? So what do we do? So what do? We go in and we add a 2 over here. So now we've got 4 hydrogen on the side and 4 oxygen. And we've got 2 hydrogen and 2 oxygen. So we just add a 2 here. And now we've got 4 hydrogen and 4 oxygen and 4 hydrogen and 4 oxygen. Now my equation is balanced. Okay, 6.1.2. How would a catalyst affect the reaction? A catalyst will lower the activation energy of the reaction. So the catalyst increases reaction rate, it increases how fast it happens, how easily it happens. It doesn't participate in the reaction, it's not used up in the reaction. And yeah, it makes it so that more molecules can participate in the chemical reaction. It makes sure more molecules have enough energy to participate in the reaction. Okay? And then 6.1.3, use the information on the graph to calculate the mass of hydrogen peroxide that decomposed. Okay, well, this is a stoichiometry question. I don't know how comfortable you guys are with stoichiometry. But let's take a look at the information they've given us. They've told us that we have 600 centimeters cubed of O2 at the start of the reaction. Okay, and there's actually only one formula that works with this molar volume value, your Vm or your molar volume. And the only formula that works with it is this one. Moles is equal to volume over molar volume. So if you see that Vm, that molar volume value that they've given you, that should be a massive indication of what you're supposed to do, or at least which formula you're supposed to use, right? They've given it to you here. So they're basically telling you which formula you're supposed to use. So you say N is equal to volume over molar volume. So they don't actually want the mass of they don't actually want the mass of oxygen, but we only have information about oxygen. So we need to start by getting the number of moles of oxygen, which we can do easily with this formula, and then we do our stoichiometrical calculations where we compare our ratios. So I'll show you. So let's first convert this into moles. So how many moles of oxygen did we start with? So we started with 600 centimeters cubed on the graph, and they've given us our molar volume in decimeters cubed. So our SI unit is decimeters cubed, which means we need to convert our centimeters cubed into a decimeter cubed value first. Okay, and the way we do that is we are dividing our centimeters cubed value by 1,000 to get our decimeter cubed value. So it's 600 divided by 1,000. Okay, I'm not going to substitute that in like that. I'm just going to substitute it in as a number. But you plug that in on your calculator. You say 600 divided by 1,000 gives you 0.6 because we need them in the same units, guys. We can't compare centimeters cubed and decimeters cubed, okay? And then we divide by 24.45 because that's already in decimeters cubed. And that gives us a number of moles equal to 0.0245 moles of O2. So now we say to ourselves, okay, well, That's how much oxygen reacted, because pretty much, or that's how much oxygen was formed, okay? Because hydrogen peroxide is being decomposed into water and oxygen. So this is how many moles of O2 were formed. So now we do our ratio. Okay, we use our balanced equation. Here's your balanced equation. And we say, okay, well, what is the ratio of H2O2 to oxygen? Okay, and our ratio is 2 to 1. So you do that by checking your stoichiometrical coefficients. What is the coefficient in front of H2O2? It's 2. What is the coefficient in front of O2? Nothing, which means it's 1. Okay, so if they exist in a ratio of 2 to 1, it means we need double the amount of H2O2 for every same amount we have of oxygen. So if we have 0.0245 moles of oxygen, and what does that X correspond to? So you cross multiply, X is equal to, and we multiply our value by 2, which gives us a value of 0.049 moles of H2O2. So that's the number of moles of H2O2 that we started with. What did they ask for? They said use the information on the graph to calculate the mass of hydrogen peroxide that decomposed. So we know how much hydrogen peroxide decomposed in moles, but we don't have it in a mass. So how do we convert it to a mass? Well, we use our N is equal to, our number of moles is equal to small m, otherwise mass, over big M, which is molecular mass. So number of moles is equal to 0.049. Mass is what we're looking for, over the molar mass of H2O2. So remember I told you, you go to your periodic table and H is 1. Our approximate relative atomic mass is where we get our molecular mass values. For hydrogen it's 1, and for oxygen it's 16. So what is the formula for for hydrogen peroxide? It's H2O2. So we plug in. Hydrogen relative atomic mass is 1, but we have 2 of them. So we say times 2 plus relative atomic mass for oxygen is 16, but we have 2, so we multiply by 2. So it's 0.049 is equal to mass over 2 plus 32, which is 34. You solve for small m, so 0.049 multiplied by 34 gives me 1.666 recurring grams, which can also be written as 1.67 grams. So what was the mass of hydrogen peroxide that decomposed? 1.67 grams of hydrogen peroxide decomposed. Okay, I hope that made sense. Sorry, I was just taking a second to kind of clear the space so we can answer the questions a bit more easily. Now we move on to 6.2. Okay, so 6.2 says in an experiment, a learner adds 500 centimeters cubed of hydrochloric acid with a concentration of 0.36 moles per decimeter cubed to 1.2 grams of magnesium in a test tube. She records the change in the mass of magnesium as the reaction proceeds at regular intervals. The balanced chemical equation for the reaction is, okay, so it says it's balanced, you don't have to worry about it. If a reaction has stoichiometrical coefficients in it, it has to be balanced. They can't half balance it. So if it's got stoichiometrical coefficients already, it means it's balanced and you don't have to worry about it, okay? Don't worry about them half balancing it. They can't half balance it. If it's balanced, it's balanced, okay? So it says, the change in the mass of magnesium during the reaction is shown on the graph below. So you can see we start with a large mass and then we end with no mass. It ends with 0. Okay? So 6.2.1, identify the limiting reagent in this reaction. Give a reason for your answer. Okay, guys, well, something that I can tell you is that with limiting and excess reagent questions, the limiting reagent is always used up completely in the reaction. Remember, the other agent is called the agent in excess because there's always more of it than you need. So the agent in excess will always have some left over at the end of the equation or at the end of the reaction. Okay, so you can see from the graph, as I've described, that we start with 1.2 grams of magnesium and we end with nothing. So it means that magnesium is the limiting reagent because it is completely used up during the interval or the course of the chemical reaction. Okay, and the official answer on the memo is magnesium, as the mass of magnesium after 3 minutes is 0. So in other words, magnesium is completely used up. There's nothing left. You can't be an agent in excess if there's nothing of you left at the end of the reaction. So your answer here is magnesium, because at the end of the reaction time, there's none of it left. It's all used up. Okay, its amount in grams is 0. Okay, now it says 6.2.2, calculate the number of moles of unreacted hydrochloric acid in the test tube after 3 minutes. Okay, so we first need to determine, okay, well, if 1.2 grams of magnesium is completely used up, we need to first determine how much HCl that will use. So what do we say? We say N is equal to small m over big M. N is what we're looking for. Mass was 1.2. Okay, it's mg just on its own. So that's all we need for the molecular mass. So all we have to do is go find our periodic table and to identify the relative atomic mass number. And my relative atomic mass number for mg is 24. That's perfect. So we go back and we say divided by 24. My number of moles is equal to 1.2 divided by 24 equals 0.05. So 0.05 moles of Mg reacted. And I can say that it fully reacted because all of the magnesium was used up. So I know all of that reacted. Okay? So now we say to ourselves, okay, well, with our balanced equation, what is the stoichiometrical ratio between my Mg and my HCl? Okay, so Mg to HCl. So remember, at the moment, we are calculating how much HCl reacted. We know it's in excess, okay? But we need to know how much reacted before we can figure out how much is left at the end of everything. So we know that the ratio based on our balanced chemical equation is 1 to 2. Why do I know that? Because the stoichiometrical coefficient in front of Mg is nothing, which means it's 1. And the stoichiometrical coefficient, which is the big number in front of HCl, is 2. So it's a ratio of 1 to 2. So if I had 0.05 moles of Mg, how many moles of HCl reacted? So I cross multiply, and 0.05 multiplied by 2 gives you 0.1 is equal to X. And this is moles of HCl that reacted. So we know how much reacted, okay? They said that they want to know the number of moles of unreacted. So we need to first go and find out, okay, well, if this is how much reacted, how much did I start with? And then I can subtract them. So 500 centimeters cubed of hydrochloric acid with a concentration of this was added. So you already know you can convert a concentration and a volume into moles. So you say C is equal to N over V. Okay, your concentration is 0.36 moles per decimeter cubed. So you plug that in as your concentration. Moles is what you're looking for, and volume is the other value that you have. But centimeters cubed is not our SI unit, decimeters cubed is our SI unit. So we need to convert this to decimeters cubed, and we do that by dividing by 1,000. We divide 500 by 1,000 and we get 0.5. So we can go and we can now substitute in our volume as 0.5 decimeters cubed. We solve and we get 0.18 moles of HCl added at the start of the reaction. So this is how many moles was added at the start of the reaction. And this is how many of HCl. This is the number of moles of HCl that was added at the start of the reaction. And this is the number of moles of HCl that was used. So what do we do to get the unreacted? We say moles added minus moles reacted equals moles unreacted. So we take our number of moles added, which was 0.18, that was the value we got over here, and we minus the moles that reacted. So we say 0.18 minus 0.1, which means that the moles unreacted is 0.08 moles of HCl unreacted. And that's your answer to 6.2.2. 0.08 moles of HCl were unreacted or were in excess and left in the tube at the end of the experiment. Okay, so that was our answer for 6.2.2. I hope that made sense. Now we move on to question 7. Okay, so question 7 says the equation for the combustion of butane gas is given below. Define the term activation energy. So here's your definition for activation energy. Activation energy is the minimum amount of energy needed for a reaction to take place. Remember, you should have an official list of definitions that you should learn off by heart, okay? Um, there should be a grade 11 and a grade 12 version of the document. You either need to go find it online yourself or you need to ask your teacher to give it to you, okay? So that was 7.1. 7.2 says, is the combustion reaction of butane exothermic or endothermic? Give a reason for your answer. Okay, well, we already did something about this. Remember, I told you that if it's endothermic, it means your change in enthalpy or your change in H is going to be positive or bigger than zero if it's endothermic, and your change in enthalpy is going to be negative or smaller than zero if it's exothermic, okay? So you can see here that change in enthalpy is smaller than zero, which means it's negative, which means that this reaction is exothermic. Okay, the reason is we have a negative change in enthalpy, but you also need to know, you can also just have guessed that because a combustion reaction, which is defined as the burning of a fuel in excess oxygen to produce carbon dioxide and water, it will always be an exothermic reaction because it releases energy. A release in energy is known as exothermic, okay? The official answer on the memo says an exothermic reaction releases energy and therefore has a change in enthalpy that is lower than zero, which you just got from this over here. You can see change in H is smaller than zero. If something is smaller than zero, it's negative. Okay. Then it says 7.3, draw a sketch graph of potential energy versus course of reaction for the reaction above. Clearly indicate the following on the graph: the activation energy, the heat of the reaction, and the reactants and the products. Okay, so this is your typical graph used to basically show you the difference between endothermic and exothermic. So I'm going to draw the graph you needed for this one. So this is for an exothermic reaction. Remember, they specifically told you what they wanted you to indicate on the graph. So you know that this is your y-axis, this is your x-axis, this is time, and this is potential energy. Sorry, I can't write the whole word potential energy skew like that. So PE stands for potential energy. This is time. And now we indicate on the graph all the things that they were looking for. Obviously, you need to draw these all in appropriate colors You can't just use any color you want. I'm just I'm just doing it in different colors because it makes it easier to kind of see what's going on. And there's your exothermic graph. You've got a heading saying that's for an exothermic graph. You've labeled your x-axis as time. You've labeled your y-axis as potential energy. You've indicated that your change in enthalpy is between the potential energy of your products and your reactants and your products. You've indicated that your activation energy is between the line of your reactants and your peak on your graph. And you've labeled that reactants are on the left hand side and your products are on the right hand side. So this is the graph they're looking for. Okay, you need to go and study the structure of the endothermic graph as well. Okay, more study work. Okay, and then it says determine the empirical formula of butane gas if it consists of 82.76 carbon and 17.24% hydrogen. Okay, this one, it seems difficult, but it's actually not too difficult. I'll explain now. So, how do we determine this? When they give you these values in percentage, okay, like this, and it's 100% sample that they've given you. Is 82.76 plus 17.24 100%? Yes, it is. Then all that we do is we assume that the sample that we're working with is 100-gram sample. Because it's 100% describing carbon and hydrogen, we assume that it's a 100-gram sample. So we start by calculating moles of each one, okay? And we assume that this 82%, we assume that it's equivalent to 82.76 grams. We assume that it's 82.76% of a 100-gram sample. So then we say, okay, well, our mass, according to our assumption of carbon, is 82.76 divided by my molar mass or my big M value. Because remember, this is the formula we're using, small m over big M. And big M we get from the periodic table. The relative atomic mass number of carbon is 12. So that means the number of moles that we get for this one is 6.896. Then we do the same thing for hydrogen. We say N is equal to 17.24% because we're assuming a 100-gram sample divided by my molecular mass or molar mass of hydrogen, which is 1, which is equal to 17.24 moles. Now, to get a ratio, we need to take our smallest number, which is this one, and we divide both values by our smallest number. So we divide by 6.896, divide by 6.896, and that's going to give us a ratio of carbon to hydrogen of, if I go and I divide, what happens when I divide 17.24 by 6.896. I get 2.5. So it's a ratio of 1 to 2.5. But remember earlier I said to you that we don't really appreciate decimal numbers. We don't appreciate decimal values in a ratio. Okay, it's not accepted. Fractions and decimal values are not acceptable when it comes to ratios. We want whole numbers. Ratios are whole numbers. So how do I get rid of 0.5? I multiply by 2. You do whatever you need to do to get rid of the decimal, and whatever you do on that side, you need to do to the other side. So our ratio then, to get it into whole number forms, become 2 to 5. So that means that your empirical formula is C2H5. And that is your answer for 7.4. Okay, that's great, because that means we can now move on to question 8. Okay, question 8. Two reactions of sulfuric acid are shown in the diagram below. So here we've got H2SO4 plus NaOH giving us salt X and product Y. And here we've got H2SO4 plus H2O in reaction 2 giving us amphilite A plus H3O positive. Remember, amphilite describes a substance that is capable of acting as either a base or an acid. So an amphilytic substance can act as either a base or an acid by either accepting or donating a proton, otherwise known as an H positive ion. Okay? So the first question, however, says define a Lowry-Bronsted base. Okay, well, according to the Lowry-Bronsted theory, a base is a proton acceptor. That's the official definition. Like I said, you need to go get the official list and learn them off by heart. Okay? 8.1.2, write down a balanced equation for reaction 1. So you can see they're asking for a balanced equation of reaction 1. Here they say H2SO4. This is reaction 1. It's reacting with NaOH to give us a salt and product Y. Okay, so remember, when a strong acid reacts with a strong base, they react to give us a neutral salt and water. So product Y has got to be H2O. Okay, and our salt will have to be, you see, one of these H's bonds to form H2O with this, which means our salt is going to be NaSO4. But the charge on SO4 is 2 minus, and the charge on Na is +1. And remember, the charges swap. So the positive 1 charge goes to here, and this becomes SO4, just 1. But the 2 minus charge on the SO4 goes to the bottom here and makes this Na2SO4. Okay, but we don't know now if this is balanced. Okay, so they're going to want multiple things from us. They're going to want our state of matter, little descriptions here. So we say aqueous, because remember they have to be, in the ionic form. NaSO4, this can be liquid, this can be aqueous, because it's floating around in water. Okay, but it's not necessarily balanced. I'm not going to go into detail with the balancing of the equations. I've shown you how to balance in some other videos. So you know that you just need to go and establish that you have the same number of atoms of H, S, O, and Na on the left-hand side as you do on the right-hand side. So we just go in with our balancing numbers, and that is your equation. I'm sorry it's a bit messy here. This is just the states that I've given here, aqueous. So it's H2SO4 aqueous plus 2 NaOH aqueous gives us Na2SO4 aqueous plus 2 H2O liquid. So that's the answer for that one. That's the answer for 8.1.2. 8.1.3, write down the name of the salt represented by X, okay? They don't want the formula, but this is the salt. So what is the name of the formula of the salt? And the name is, because sodium and SO4 is sulfate. Sodium sulfate. That is the answer to 8.1.3. Sodium sulfate. Okay, now we go to our next one, H.1.4. Write down the formula for ampholyte A. Okay, so remember I told you an ampholyte is a substance that can act as either a acid or a base. So it can either donate or accept a proton. Okay, so they're asking what is ampholyte A? Okay, so you know that it's got to be some form of H2SO4 because that's what we're working with. That's what's got to be here. Okay, and you can see that H2O has gained a proton. It's become H3O positive. So you know that you need to give the version of H2SO4 that has donated one of its hydrogens to water. You need to give the version of H2SO4 that has donated a hydrogen so that water, H2O, could become H3O positive. The only way water becomes H2O, the only way H2O becomes H3O positive is if some other substances donate an H positive. So the formula of ampholyte A is going to be H So 8.1.4 is HSO4 negative. Okay, so now we move on to 8.1.5. Write down the formulae of the two conjugate acid-base pairs in reaction 2. Okay, and your conjugate base pair, like, so they're not actually asking you to specify which one is which, they're just asking you to tell them which were the reaction pairs, okay? And the reaction pairs were H2SO4 and HSO4 minus. This is my acid and my conjugate base. Why? Because my acid donates a proton, because you see it has lost a proton in this format here. Okay, and why? This is our base and our conjugate acid. Why? Because H2O accepts a proton from H2SO4 to become H3O positive. So that's all you need to do. You just write HSO4 negative and H2SO4 and H2O and H3O positive. Okay, and those are your conjugate acid base pairs. And I just wanted to, I kept this image here from one of the previous videos so that you could just have a look. A base with its conjugate acid. So here the base accepts the proton and becomes the conjugate acid. Here the acid donates the proton and becomes the conjugate base. Okay, now we move on. Now we move on to 8.2. Okay, so 8.2 says a solution of sodium hydroxide is prepared by dissolving 6 grams of solid NaOH in 500 centimeters cubed of water. The solution reacts completely with 10 grams of impure ammonium chloride, according to the equation below. Okay, I don't see any balancing numbers, so we need to check that it's balanced. That's step number 1. Okay, so let's see, it says we've got 1 Na, 1 O, 1 H, we've got 1 N, and that's 5 H's and 1 Cl. 1 Na, 1 Na, 1 Cl, 1 Cl. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 1, 1, 1. So our equation is balanced because we have the same number of atoms on the left-hand side as we do on the right-hand side. So nothing further is needed for this equation, so we can use it as it is. So it says calculate the concentration of NaOH solution. Okay, well, concentration is equal to moles over volume. Okay, so they said they want the concentration of NaOH. A solution of sodium hydroxide is prepared by dissolving 6 grams in 500 centimeters cubed of water. So we first need to turn our mass into moles. So we say our mass is it's 6 grams over my molecular mass, and it's NaOH. So I know hydrogen is 1, I know oxygen is 16. I need to go double check what Na is. I go back up to my periodic table. What is Na? Na is 23. So it becomes 6 divided by we say 1 plus 16 plus 23. So it's 6 divided by 40. So what is the number of moles that I have? I have 0.15 moles of NaOH. So I go and I say, okay, cool, well, 0.15 moles over my volume. Okay, remember your volume needs to be in decimeters cubed. We've got it in centimeters cubed. So we need to divide by 1,000 to give us to give us 0.5 decimeters cubed. And so my concentration is equal to 0.15 divided by 0.5, which gives us 0.3 moles per decimeter cubed of NaOH. And that's correct. That's your final answer. So that's for 8.2.1. Then we move on to 8.2.2. So calculate the percentage impurities in the NH4Cl. Okay, so how are we going to go about this? We are going to say to ourselves, okay, okay, so it's saying that everything reacts completely. It's just that your ammonium chloride was impure. So it means that you need to determine how much reacted based on the number of moles that you just calculated for NaOH. So the number of moles that you just got for NaOH was 0.3. Oh no, sorry, that was your concentration. That was your concentration. Your concentration was 0.3 moles per decimeters cubed. But you already calculated that N was equal to 0.15 moles. So you know that 0.15 moles of NaOH reacted completely because it says that the reaction ran to completion. Okay. And it says that the only one that had impurities was the ammonium chloride. So we say, okay, well, what is my reaction ratio for NaOH to the substance that we're interested in? What are we interested in? We're interested in the ammonium chloride. So we say NH4Cl. So what is the ratio? We said it's balanced, so it's got a ratio of 1 to 1 because they both have missing stoichiometrical coefficients. If there's nothing there, it means 1. So 1 to 1, which means I have 0.15 moles of NH4Cl because they react in an identical ratio. So now all we have to do is convert our number of moles of NH4Cl into a mass. So we say N is equal to small m over big M, or my molar mass. Okay, so I say 0.15 is equal to the mass is what we're looking for, and now we need to get the molecular formula for NH4Cl. Okay, well, N is 14, H is 1, but I've got 4 of them, so I say 1 times 4, and Cl is 35.5. I just want to go check that quickly on the periodic table. If you do enough of these calculations, you'll eventually start to memorize them. So, see, nitrogen is 14, hydrogen is 1, Chlorine is 35.5. So those are where I got my molar mass numbers from. So I do this, I manipulate it so that I can plug it into my calculator. And when you are getting a total for your molar mass, it's going to be 14 plus 4 plus 35.5, which is going to give you a total of 53.5. So 0.15 times 53.5 gives us a mass of 8.025 grams of NH4Cl. So this is what reacted. Okay, they said that 10 grams of impure was added. So if 10 grams was impure and 8.025 reacted, remember only the pure stuff will react, which means that our impurities were the equivalent of 1.975 grams. Okay? But they didn't say that they just wanted a mass. What did the question say? The question says calculate the percentage impurity. Okay? So that means that you have to take the percentage. This is what was impure. You need to divide it by 10 grams that you started with and multiply by 100. So your percentage impurity is 19.75%. Okay? And that is your answer for 8.2.2. Okay, we're getting close to the end, guys. Let's do question 9. So question 9 says, the reaction between dichromate and iron in an acidic medium is given below. Determine the oxidation number of chromium in Cr2O7 2. Okay, so when they're asking you for the oxidation number, it generally means that they're asking you to do a small calculation to determine what the charge on chromium was. Okay, so you know that the overall charge of this molecule is -2 because it says it there. Okay, and if the charge number on oxygen the charge on your oxygen ion is also -2. Okay, so when you're doing oxidation numbers, like I said, you're determining the charges on those values by themselves, okay? So we don't know what the charge of Cr2 is. We're looking for that, okay? But we know the charge on oxygen is -2, okay? But I have 7 of them, so I multiply by 7. So -2 is the charge on the overall molecule, because that's what we have here, is equal to -2 times 7 is -14, plus, what is my Cr value that's going to get this to -2? Okay, so I take this over and it becomes positive. So positive 14 minus 2 equals Cr2, gives me positive 12 is equal to Cr2. But I just want Cr on its own. I want the oxidation number of chromium, just Cr, not Cr2. So I divide by a Cr ion on this side, or I divide by 2 on this side, and I divide by 2 on this side, and I'm left with the charge on chromium as positive 6. That's the oxidation number for chromium. Okay? So you're just using your charge values and you're multiplying them by the number of atoms that you actually have. The next question says define reduction in terms of electron transfer. Okay, well, reduction is the gain of electrons. In terms of electron transfer, reduction is the gain of electrons. Okay, write down the formula of the substance that undergoes oxidation. Explain the answer in terms of oxidation numbers, okay? So this is 9.3. The substance that undergoes oxidation is Fe2 positive, okay? And the reason for this is because it goes from Fe2 positive to Fe3 positive, okay? And you know that oxidation, oil, rig, oxidation is the loss of electrons, which means when you're losing electrons, you're becoming more positive. And in this scenario, Fe2 becomes Fe3 positive. So Fe becomes more positive and therefore undergoes oxidation. Okay, so the answer is Fe2 positive because the oxidation number increases from positive 2 to positive 3. So the one that becomes more positive undergoes oxidation. Okay, perfect. I hope that made sense. Okay, write down the formula of the oxidizing agent. Remember, I told you the oxidizing agent is the one that undergoes reduction. So it is the one that gains electrons or becomes more negative. Okay, so you can see that we calculated what the oxidation number for chromium was in this format. It was positive 6 on this side of the equation. And on this side, it's Cr3 positive, which means that it has lost some positive charge to become 3 positive. A loss of electrons is synonymous with reduction. A loss of electrons is synonymous with oxidation. Okay, sorry. I think my brain has been working for too long now, and so I think I'm making small mistakes or small errors in what I'm saying. Sorry. So, like I said, just to start again, remember that when you see the word agent, it means you're looking for the opposite of the first word. So, an oxidizing agent is the one that undergoes reduction. Reduction is the gain of electrons, which means that something is becoming more negative, okay? We already calculated that chromium's oxidation number at the front or here in this format was positive 6. And we can see that on the other side of the formula, it becomes Cr3 positive. This means that chromium has gained electrons because it has become less positive. It used to be positive 6, now it's positive 3. So it's obviously gained electrons to make it less positive. A gain of electrons is reduction, okay? And reduction is associated with the oxidizing agent, okay? So our answer here is Cr6 positive or Cr2O7 2 minus. Okay, then the next question says write down the redox half reaction. Okay, so this information you are going to find on your formula sheet. You are going to go to your table of standard reduction potentials and you are going to look for the half reaction of Cr2O7. So we start looking. Cr2O7. Okay, so it's not in its full format, but this isn't the correct one because you're looking for Cr6 positive becomes Cr3 positive. So that's not the correct one. So let's go on to the next page. Again, another Cr, but we're not looking for that one. So we keep looking. Again, not the right one because we're not looking for it to go from 3 to 0. And here it is. Just takes you a minute to find it, but here it is. They asked you to write out the half reaction, and this is it. Okay? You write it out exactly as it is here because it starts as Cr2O7 in the equation as well. So you write Cr2O7 2 minus plus 14 H positive ions plus 6 electrons gives us 2 Cr3 positive plus 7 H2O. So this is your answer to question 9.5. You just get it directly from your standard reduction potentials table. Okay, now it says write down the net balanced ionic equation for the reaction using the ion electron method. Okay, so here you're going to have to write down your reduction half reaction and your oxidation half reaction, and you're going to have to balance them. So you already know that your reduction half reaction is Cr2O7 2 minus plus 14H positive plus 6 electrons gives you 2Cr3 positive plus 7H2O. Okay, so that's reaction number one. Reaction number two is going to be your oxidation half reaction, and we've already determined that iron is the one that undergoes oxidation. Okay, and it moves from Fe2 positive to Fe3 positive. So you go and you find that Fe2 to Fe3 positive reaction on your table, and you'll find that it goes like this. Fe2 positive goes to Fe3 positive plus 1 electron, plus 1 electron. Okay, now the problem when you're trying to balance these reactions is that you need to have the same number of electrons in reaction number one on the left-hand side of the equation as you do on the right-hand side of the equation in your second reaction, okay? And the only way you can do that is by multiplying one of the reactions by a lowest common variable. And that is multiplying this entire reaction by 6. So you're going to multiply this by 6 and this and this. So this one basically becomes 6 Fe2 positive gives me 6 Fe3 positive plus 6 electrons. Now your electrons from equation number 2 will cancel out with the electrons from equation number 1 because I've got 6 electrons on the left and I've got 6 electrons on the right, so they cancel each other out, okay? And now we just write it as one complete equation. You write everything that's on the left-hand side in this equation that's left over, plus this side, with everything on this side, plus this side. So we go. Okay, so Cr2O7 minus, that's still there, plus 14H positive. (14H positive), that's what I just got there, right? Plus, now I get to the arrow, so now I'm still need to get what's on this side. Plus 6Fe2 positive. Now our arrow comes in. Now we take everything that's on this side plus everything that's on this side. So we say 2Cr3 positive plus 7H2O plus 6Fe3 positive. And that's your final answer. Cr2O72 minus plus 14H positive plus 6Fe2 positive gives me 2Cr3 positive plus 7H2O plus 6Fe3 positive. And that is your final balanced equation. And that is the answer for 9.6. Okay, now we move on to question 10. So question says, gold and iron are two of many minerals mined in South Africa. Iron is mined in open cast mines while gold is usually found in deep shaft underground mines. During the process of refining, the following chemical reactions take place to extract the metal from the ore. Gold is dissolved in a solution that contains cyanide ions to extract it from the ore. The balanced chemical equation for the reaction is, and this is the reaction there. Then iron 6 oxide and carbon are heated in a furnace to extract iron from the ore. The balanced chemical equation for the reaction is 2Fe2O3 plus 3C gives me 4Fe plus 3 CO2 gas. So this is again a study question. I'm not so sure how relevant this is to grade 12. Um, you'll have to check with your teachers in terms of how in detail you need to know the mining chapter. I think it becomes the chemical industry chapter in grade 12. So you might just want to double check with your teacher. Again, guys, this is all study work. It should come from a book. So go and look at those textbooks that I suggested earlier online if you feel like you are really lacking in the theoretical knowledge for these questions. But the answer for 10.1, state 2 advantages of open cast mining when compared to deep shaft or underground mining. Miners do not have to risk their lives going deep or being trapped underground, and there is no risk of sinkholes. So advantage number 1 is that miners do not have to risk their lives by going deep underground or getting trapped underground. And advantage number 2 is that open cast mining does not risk the formation of sinkholes. Okay, 10.2, or consider the iron extraction reaction. 10.2, is iron oxidized or reduced during the reaction? Give a reason for the answer. So here we're looking at the iron extraction. Okay, so they're saying in this, I've already showed you now how to determine if something is being oxidized or reduced. You need to first determine what is the charge on the one side of the reaction, what is the charge on the other side of the reaction, and then you determine, are electrons being lost? Is this becoming more positive through the chemical reaction, or is it becoming more negative? Is it gaining electrons? Okay. And if you take a second, you will see that iron is undergoing reduction, okay, because its oxidation number decreases from 6 positive to 0. So you can see over here that Fe2O3, you know that the charge on O is 2 minus, okay? So that's going to be 3 times 2 minus is going to be negative 6. So whatever the charge is on this Fe needs to counteract the charge of this one to give us an overall charge of 0, because you can see that this is a neutral atom. There's no charge here in the top right hand corner, which means that the 2 iron molecules here are positive 6, and they're going from being positive 6 to being 0 over here. They've got no charge over here. Remember, you need to use your oxidation number formula or kind of technique to determine what the charge is here. But the point is that the charge on iron is going from positive 6 on this side to 0 on this side, which means that electrons have definitely been gained and reduction has occurred. So that's 10.2. 10.3 says state 2 disadvantages of using carbon in this reaction. Again, this is studying. You can't just know this. But number 1, carbon is a non-renewable resource. 2, carbon dioxide is a product and contributes to global warming. So what are the 2 disadvantages of using carbon? Number 1, carbon is non-renewable, which means eventually we're going to run out of it. Okay. And number 2, carbon dioxide is produced during this reaction, which contributes to global warming. Okay. Now it says consider the gold extraction reaction. Okay, so that's this one at the top here. It says, give one reason why gold is present as an element in the ore. Okay, again, this is going to be study work. 10.4. The gold does not oxidize easily like iron. So gold doesn't easily lose electrons, okay? And that's your answer. The gold does not oxidize easily like iron. And then 10.5 says, what role does oxygen gas play in the reaction? and oxygen gas acts as an oxidizing agent. And remember, oxidizing agent means that it undergoes reduction. Okay, cool, guys. This was a really long session. I hope it helped, and good luck with your studying.